This lesson will prepare you for the acid-base and acid-base equilibria unit in AP Chemistry. We will review topics such as the definitions of acids and bases, the strength of acids and bases, and the pH formulas. There will be some things that are review from grade 11, and there will also be some new topics that are specific to the AP course. The first thing that we'll do is discuss the definitions of acids and bases. And there are 3 definitions of acids and bases, each becoming more and more broad in their ability to help us understand acids and bases. Although we have 3, each have their own specific uses as well. The first definition of an acid and base is the Arrhenius definition. By Arrhenius, an acid is a substance that dissociates to produce H+ ions in solution. And the way that you can recognize an Arrhenius acid is by the hydrogen at the beginning of the formula. So for example, hydrochloric acid is a classic Arrhenius acid. When it dissociates in water, it produces H+ and Cl-. Bases, by Arrhenius' definition, dissociate to produce hydroxide ions in solution. And you can recognize an Arrhenius base with the ionic formula composed of a metal and a hydroxide ion. So sodium hydroxide fits this definition well, as it dissociates in water to produce sodium ions and hydroxide ions. Now it's important to note that it's the H+ and the OH-, or the hydrogen and the hydroxide ions, that are responsible for the properties of these substances. Properties such as acids react with metals to produce hydrogen, acids react with litmus to produce a red color, or they're clear in phenolphthalein. Bases, on the other hand, react with litmus to produce blue, or react with phenolphthalein to produce a pink color. By Arrhenius' definition, the acid-base reaction is a simple one, where an acid plus a base produces a salt and water. And it's important to note here that the salt is not just sodium chloride, it's any salt or an ionic compound that can be produced here. The Bronsted-Lowry definition of an acid and base is a bit broader, and it covers some of the flaws in the Arrhenius definition. One of the flaws from the Arrhenius definition is that H+ ions don't actually exist on their own in water. They exist as H3O+. So you'll see from the Bronsted-Lowry definition that we see H+ in our reactions rather than H3O+. The other flaw with the Arrhenius definition that is corrected with the Bronsted-Lowry definition being broader is that there were some bases or substances that had the properties of bases that didn't reflect the definition very well. So we'll look at an example in a moment. The Bronsted-Lowry definition of an acid and base involves protons. And when we look at a proton in chemistry, what we're talking about is an H+ ion. What you can remember is that hydrogen has 1 proton and 1 electron. So when it becomes H+, what we're left with is a bare proton in solution. So that's why we call H+ a proton. Now, by this definition, an acid is a substance that donates a proton, and a base is something that accepts a proton. When we look at these substances and their reactions in water, what we need to do is look at the substance. So in this example here, we're looking at vinegar, and we're adding water. These reactions are always going to be equilibrium reactions, which we'll discuss further as we go along. Now you can recognize a Bronsted-Lowry acid as one that usually has this Cu group at the end. So you'll remember from grade 11 organic chemistry, this is the carboxylic acid group. And it's this hydrogen at the end that's the acidic proton. If we were to draw a picture of this molecule, we've got CH3 and then COO H. The hydrogens that are attached to the carbon are not acidic, okay, so they will not be donated. But this hydrogen here is acidic. It's able to be donated to the water molecule. The reason for that, okay, is related to the structure here. These oxygen atoms are more electronegative. They pull the electron density away from the hydrogen, weakening this bond and allowing it to be broken. So what we have here is we've got this hydrogen being donated to this water molecule. And so the vinegar molecule is losing a proton, so we're taking away an H+. We're left with a negative acetate ion. And the water molecule, I'm adding H+, and we're left with H3O+. A Bronstead base is a substance that accepts a proton. Ammonia, NH3, is a classic and the most basic of the Bronstead bases. So it's really important that you know the formula for ammonia, which is NH3. Now, most Bronstead bases, structurally, what you'll find is that they have nitrogen in them. They're sometimes referred to as nitrogen bases. The reason that they're able to accept a proton structurally is because they've got this lone pair of electrons on the nitrogen. So what you'll see is that the formulas will usually have carbon and hydrogen in them, but they'll often have nitrogen as well. And what you'll see is that whenever the proton is being accepted by the base, it's always being accepted at the nitrogen. So the hydrogen comes in here, okay, and these are actually the electrons that are used to form the bond. So what happens here is that the water is the donor in this situation. It's donating a proton to the ammonia, and we're left with the ammonium ion and hydroxide. Now this is an example of one of the bases that didn't fit the Arrhenius definition of a base. Although ammonia had basic properties, so it would turn phenolphthalein pink, for example, the formula didn't fit the definition. And it was impossible for chemists to see how this substance, when in water, dissociated to produce hydroxide ions. But as you can see from this broader definition, we do see that hydroxide ion present in the solution that is really responsible for the properties. Now you may be wondering why water in this situation is accepting a hydrogen ion, and in this situation it's the donor. This is what is called an amphoteric substance. So water has the ability to act as an acid or as a base, and it will change depending on what other substances are present. So in the case of reacting with vinegar, because the vinegar is more acidic, the water is forced to act as a base. While in the second example, the water is the more acidic of the two, so it's the one that donates the proton. Other examples of amphoteric substances are common polyatomic ions. So as you can see, this HSO4-, it has a hydrogen for donation, so it would be able to donate this. And it's also an ion and would be able to accept a proton to become H2SO4. So this is what an amphoteric substance is. Now these two reactions are both examples of acid-base reactions using the Bronsted-Lowry definition. They both involve the donation of a proton from one species to another. And that's what the definition is under the Bronsted-Lowry. Now in the Bronsted-Lowry definition, which is going to be the main definition that we use in this course, when you write the reaction for a substance in water and have the proton transfer, you're going to be able to identify what are called the conjugate acid-base pairs. Or if you're given just a regular acid or a base, you could also identify its conjugate. The definition of a conjugate acid-base pair is a pair of two substances that differ by one proton. One of the substances is the acid, and one of the substances is the base of the pair. And the way that you identify it is by which one has the proton to donate and which one would accept a proton. So if we look at this reaction, this is the vinegar molecule again, just written a different way, and this is the acidic proton. This is the proton that's being donated to the water. This acid molecule differs by one proton from the acetate ion on this side. So they are an acid-base pair. And they are related to one another by one proton. This is the acid in the pair because it has the extra proton, and this is the base in the pair. Water and the hydronium ion are also an acid-base pair. They differ by one proton. In this case, the water is the base, and the H3O plus, or the hydronium ion, is the acid. Now you might wonder why we would even consider this. You're going to see that these reactions are all equilibrium reactions. So there's a forward process and there's a reverse process. In the forward process, the vinegar molecule is acting as the acid and the water molecule is acting as the base. And in the reverse process, the hydronium is the acid and the acetate is the base. So that's why we have them labeled on both sides of the equation. Now, when you first study water in high school, you're told that if you've got pure water that's distilled, there are no ions in the solution. When you've got regular tap water, it's got all the ions, like there's metal ions and other things in the actual water. In actual fact, when we've got a sample of water, there is actually a very low concentration of hydrogen and hydroxide ions. And this is because water molecules, being amphoteric, have the ability to both accept and donate protons. And when water molecules interact with one another, they produce the H3O plus and hydroxide ions in the solution. I'll do a demo for you next class that'll show you that in actual fact there are ions in the solution. Now this is an equilibrium reaction, and it's got an equilibrium constant associated with it. It's called Kw, the equilibrium constant for the dissociation of water. So the W stands for water. As you know, when we want to write the equilibrium law, it's the concentration of the products divided by the concentration of the reactants. Water, being a pure liquid, is not going to be included in the equilibrium law. So this equilibrium constant is H3O plus times hydroxide ions. And this equilibrium constant has a value of 1 times 10 to the negative 14, which is very, very small. So even though at first when you're studying water, you learn that there aren't any ions in solution, the reason that we discussed it in that way is because the concentration of the ions is tiny when we're talking about neutral water. The concentration of each of these ions is 10 to the minus 7, which is very, very small. When we look at a solution, it's important to identify whether it's a neutral, acidic, or basic solution. And it's neutral, as you know, if the amount of hydrogen ions is equal to the amount of hydroxide ions. In an acidic solution, the amount of hydrogen ions in the solution is greater than the hydroxide. And in a basic solution, the hydroxide ions are in a higher concentration. Now this is it's important to note that this is the way that you should be viewing acid, base, and neutral solutions. Sometimes when students are first learning about acid-base chemistry, they think of acids as being substances where there's only H3O plus and bases where there's substances where there's only hydroxide ions. But the reality is all solutions in water have hydroxide and hydronium ions in solution. It's the relative concentrations in that solution that decide whether it's an acid or a base. So if you've got something that's really basic, like very high on the pH scale, the concentration of this is going to be very high, and that's going to force the concentration of the hydronium ion to be very, very small, okay, because these always multiply to 1 times 10 to the negative 14. And that brings us to the pH scale. And as you know, low on the pH scale are the acids. Above 7 on the pH scale are the bases. And we're dealing with a neutral solution when we are at a pH of 7. Okay? And that makes sense because when you're at a pH of 7, the hydrogen ion concentrations are equal to the hydroxide ion concentrations. And so when we look at the Kw being 1 times 10 to the negative 14, that would mean that if it's neutral, each of the H3O plus and hydroxide will equal 1 times 10 to the negative 7. Okay, and we'll review this a little bit later, but the pH is the negative log. And so if you take the negative log of 1 times 10 to the negative 7, you get a pH of 7. This Kw being temperature dependent at 25 degrees Celsius aligns with the pH being 7 at 25 degrees Celsius. So technically speaking, as the temperature changes, the Kw will change, and therefore the pH of neutral might slightly modify. Okay? It's a very, very small difference. So generally speaking, this pH scale is fine to use. The next very important topic in studying acids and bases is to understand the difference between a strong acid or strong base and a weak acid or weak base. And this understanding is really going to control how we approach many of our calculations. I've already asked you to memorize the strong acids and bases. This is key to being able to do many of the calculations that are coming up, is to know and be confident in your knowledge of the strong acids and bases. By definition, a strong acid is something that dissociates completely. So when we're dealing with strong acids and bases, we're dealing with complete arrows. And these really fit the Arrhenius definition of acids and bases. So these are the strong acids, and anytime you're dealing with one of these acids, this is how they will behave when they're in water. They simply dissociate completely to produce H plus and the counter ion. The strong bases also dissociate completely. They are salts formed with the metals from what I refer to as the big little b on the periodic table, and hydroxide ions, and those dissociate completely. So this is a visual here. Okay, if we start with this amount of hydrochloric acid molecules at equilibrium, or once we've allowed it to complete its reaction, we will have the exact same amount of H plus and Cl minus. So the molecules will be fully dissociated in the solution. When we're dealing with a weak acid or base, we're going to need to use the Bronsted-Lowry definition because we're going to be looking at equilibrium. A weak acid or a weak base is something that only partially dissociates in water. And you're going to see that a lot of these will dissociate less than 5%. So the way that you can recognize them is that they've got the Cu group, so organic acids tend to be weak acids. Okay? And hydrogen fluoride is another weak acid. It's not on the list. Okay? We'll discuss structurally why some acids are stronger than others. These are going to have equilibrium constants associated with them, and they'll have a small Ka value because the equilibrium does not go very far to the right. Weak bases are those organic bases that I discussed earlier. So you'll see they've got some carbon and hydrogen, okay, and then they've got the nitrogen in them, and the nitrogen is where there's a lone pair that accepts the proton. Now the key here is to understand that when you've got a weak acid or base, it doesn't dissociate completely. So when you look at the before and after, say I had 100 molecules of hydrogen fluoride to begin with, I might only dissociate 5 of those. So if it was a 5% dissociation, I would only dissociate 5 of them. The other 95 molecules would stay intact. So when you look in the solution, there's fewer H3O plus ions in the solution, okay, which is going to affect things like the pH.